Mm, Great. Let's start today class. Previous time we talked about probabilistic embedding into trees, the last session. We just briefly discussed some of the concepts that we discussed. We talk about metric spaces, in particular. A metric is some function that has the following three properties. The distance of one point to itself is 0. We have the symmetry. Distance from I to j is equal to distance from j to I. And finally, the triangle inequality, distance from I to k plus the distance from k to j is greater than or equal to distance from I to j. And as we mentioned, a metric is often represented with a pair xd essentially. X is the set of points and d is the metric function. And we discussed that generally we can consider a graph and we can consider the shortest path metric of a graph. And we talk about this when we talk about this, we talk about metric completion of a graph, which is also called metric closure. So for any graph, we can compute the shortest path. Even if the graph is not connected, still you can have the shortest path infinity, and that will be the metric that we are talking about it. Then we talk about embedding, is that we are embedding generally from one space to another space, in which solving a problem is easier. For example, L1 is some metric which might be easier for some problems, or in particular, tree metrics are the other ones which are very useful because we can solve almost all problems on trees or graphs which are similar to trees, particularly graphs of bounded trees, for example. And we talk about the contraction of an embedding and extension of an embedding, and we mentioned that we can always assume that these metrics that we are considering are expansive. What's the meaning of that? The meaning is that distances only go up comparing to the original things, and we want to minimize distortion. Distortion is that while they are expansive, we don't want to be like every distance in the new metric, f is the new metric essentially after the mapping, should be sandwiched between the original distance greater than or equal to the original distance and alpha times the original distance. And we want to get this alpha as small as possible. It would be isometric. If the alpha is equal to 1, it might be hard to get it alpha equal to 1. That's the reason that we want to embed it such that we get it as small as possible. Good. And then we talk about embedding into distribution of the trees. Why distribution of the trees? The idea was that if you have a cycle of lengths n and all of this, so this is the graph that we are considering. When we talk about graph, we always consider the shortest path metric of the graph. So if the distances are all 1 and this is the Cn, we talk about it that if you want to embed it into one tree, the distortion becomes very large, because if especially this tree is a subtree of this one, then you need to delete one edge or a spanning subtree, and the distance between these guys was 1. Now it becomes n essentially, and the distortion becomes n. That's the reason that we consider probabilistic like embedding into distribution of trees or probabilistic trees is that we didn't want to embed into just one tree, but we wanted to embed into a set of trees. Here, if we want to embed it into a set of trees, instead of, we could have essentially, as we discussed previous time, you could delete each of these edges, and then the distance with probability 1 over n. So in some sense, we had a tree T1, T2 to Tn. In each of them, we are just deleting one of these edges. And as we discussed, each of these ones have a probability. They should have a probability as well, each of these trees, 1 over n. And you can see that if we are doing that, this T1, T2 to Tn, then the distortion of this embedding would be only 2, or less than 2, actually. So in that sense, we are in a much better shape. And that's the thing that we defined about distribution trees. So again, so that was the definition. We want to embed it into a set of trees. As I mentioned, one tree was not enough, so we need to consider a set of them. And we want to have this property that the distances are, again, expansive. It means that they should go up only. And more importantly, we don't want to go that much up. In a sense, we want to sandwich. That's the thing that we talk about it, that for each of these trees, we have a probability pi. So for any two vertices in the original graph, and again, we are talking about the metric distances, so all the probabilities would be on graphs, in the shortest path metric of that graph. So in that case, the distance between any people like in this set of trees should be, like, you need to consider the average distance. The average distance would be for each of these trees, what is the distance between them times the probability of that tree. And when you take this average, it should be less than or equal to alpha times the distance in the original graph. And here, alpha again is this distortion that we want to minimize. And as again, that's the thing that I have mentioned. You can get less than 2 if you consider the CN. Then we talk about trees. So what type of trees can we have? In general, these trees that obtained here, it can be a spanning trees, or it can be like any trees. As long as they are expansive, it means that the distances between any two vertices just becomes larger than the original distance. Good. When we consider the graphs, we can always consider that this graph has some edge. If there are some edges that, like, if we have a graph like this, and for two vertices, x and y, the distance between them is greater than, like, the distance between shortest path in the graph, we can remove this one if we care about connectivity problem that we talk about it. So in that case, we can say that there is no, and we can call this edge a useless edge in the graph. So we can always delete useless edges as long as we want to connect a set of vertices that we talk about it. And we talk about that, I mean, we are, the main problem, we have the cut problem, we have the connectivity problem, and we have this kind of assignment matching problem. Here for connectivity problem, if for two vertices, I mean, their distance is greater, so this is 10, while the shortest path here, I don't know, maybe it is just 4. So then you can just delete this guy because you can connect this. So we consider a graph like this, we delete the useless edges, and say that in this graph, the best set of trees that we can get it are spanning trees of this graph, and say that the graph is connected as well. That would be somehow the best of all worlds. Why? Because we have this expansiveness, like essentially for granted. Because if we consider any subtree of this tree, subtree of this graph, the distances between any two vertices would be greater than or equal to the original things because we just take a subgraph of this. The only thing is that then what about this distortion alpha? Can we have any bound on that? That would be somehow the best things. And you can think about this when you try to solve the problem. That would be the best way to think about it. As I mentioned, there is a long history of improvement. First, the people actually considered this one. The best bound was 2 to the, I think, square root of log n, that when they considered spanning trees. Then the people considered non-spanning trees. Then for that, they got it. That was the Bartal result. That was log n to the 2. And then it was improved to log n, log n. And finally, this is the FRT factor. Paul, actually, he put, if you go to his homepage, he mentioned how you can pronounce his name. He put the way. Anyhow, this is, we call it as the FRT that we will talk here. They show that you can get log n, and log n is indeed tight. You cannot get anything better than log n when you want to embed into trees. But this result, these are not a spanning trees. There was a result by Elkin, Emek, Spillman, and Tank that they could improve this one for spanning trees to log n to the 2. And then there was some more recent work on that. Yes, so this is this result in Fox 08, a new result by Abraham, Bartal, and Neyman, that they improve the previous result of log n to the 2 to log n times log n times log n to the 3. That was a Fox 08. And it would be actually interesting. This would be a very nice open problem to see, can we get this one also log n tight and make the story very clean? Because as I mentioned, this one's slightly worse than log n, but the good thing here is that these are spanning trees, very natural set of things. So in some sense, you can think about this one is toward theory of everything, that you want to get very nice, clean, the best bound for it. And I think the correct answer should be log n even for trees. But as far as I know, this is the latest version and still we don't have log n. It would be good, I mean, to check that there is no further results on that and get it the tight result, because that would be very clean result. Like FRT comparing to Bartal, they talk about Bartal, but FRT is the one that the people are using it, and it's a very clean, nice algorithm, and so that would be very nice to get. So this was about spanning tree versus non-spanning trees. Also, another thing was like again towards this theory of everything. In the when these are not spanning trees, this FRT and the other one that was used, they may have some Steiner points. So it might, so because when you have the trees, it might be the case that you have a graph, for example, here, X, Y, Z, W, and this is like 4 vertices. So we have X, Y, Z, and W. So you can have actually a tree metric and say this is A1 and A2. So these 2 vertices are a Steiner point. They are not in the original graph, but they have been added to this tree. So it's a tree metric. You can have Steiner points. And as I mentioned, actually the way that we created even the FRT or Bartal, they may have this additional vertices, which are not in the graph. Of course, when we talk about all this kind of probabilistic embedding, we really don't care about them as long as when we consider the distance between x and y, we say, okay, this is the distance from here to here. And we just compute this distance, but not the, so we talk about the distance, but not really about other than that about the Steiner points. So in some sense, okay, these are something is not, again, not the proof from the book or theory of everything. Then what about this point? There was a paper by Anupam Gupta, I think that was in Sausage, or like around 2000, that he showed that if you have a tree metric, you can always delete these Steiner points such that the actual tree only becomes on the set of vertices that you want, and the distance between these guys, they are going at most by a factor 8 up. So it goes by constant factor up. I think this was improved 8. I'm not so sure that we have the tight results here. That's also another interesting result that is back in 2000. And as far as I know, we don't know the tight answer for this one. We know it is constant, which is enough for lots of things, but it would be good to get it clean that what is the thing. But this theorem actually cleans everything, because it says that whenever you consider probabilistic embedding into trees, then you don't need to consider like Steiner points, because you can always consider the trees on the same set of vertices that you are considering on the original graph. But still, as I mentioned, this other result by Abraham, Bartal, and Newman, that actually is a bit cleaner, because when you talk about spanning trees, then there are no such Steiner points. So in that sense, the people try to make it clean. And again, this would be very amazing, I think, result now, especially to get rid of all these log and things and then get it log n while these are spanning trees. Let me give you an example of how can we use it. I think that is important. And this is a general way that we are using it for these problems. And then I will talk a little bit about the cut problems and the corresponding cut problems that you can also use it for lots of applications. But let's start with this one. Good. So let's consider the Steiner tree problem. And we want to see how can we use this algorithm. So again, what is the idea is that you have a graph, and then we consider shortest path metric. Generally, we talk about the connectivity problems, means we want to connect a set of vertices by some constraints. We are embedding this graph into a set of trees, probabilistic trees. Each of these trees, say for now, the simplest case is that, like the best case is that each of these trees is a subtree of this original graph. So by definition, they are expansive. And each of these trees have a probability, P1 to Pn, that we consider the average distance between any two vertices on these trees. And that is at most log n. Yeah, or log n, we will talk about O tilde log n. So, but this is, so even if it is not maybe log n for spanning trees, but it is O tilde. And see what can we do here. By the way, that's also another interesting thing is the number of trees also, because these are like several parameters, that how many trees can we have it, because that would be good for running time. Like if you just do it naively, the number of trees actually can be exponential, but you can show that actually you can get it. I think this is a result of Moses Charikar, that he showed that at least on the FRT, you can get Fn log n trees. So the number of trees would be also O tilde n that you are generating. And I believe that, I mean, this is the best like even I think for the cycle, probably you can show that you cannot get much below this. Good. So the number of trees also are limited. Otherwise, the running time of the algorithm can be large. Good. So what is the Steiner tree? So you are given a set of vertices or terminals T1, T2 to Tn, and you want to connect them to a root Rs in the graph G, in which each edge has a buying cost B. So you are given a graph. You want to essentially a set of Steiner points S1, S2, S3, S4 is given for Sn, and you want to connect them essentially all. I mean, you can say there is each of these vertices is the root or not. That does not change that much the problem. Because if you want to connect all of them, of course, it is connected to the root aspect. So rooted and unrooted, there is not much difference between. So we want to solve this problem on the graph. As I mentioned, for this problem we discussed, there is the best approximation is 1.39. But we don't want to go there. We want to, and there is, I mean, simpler one like using MSD, which is 2 approximation. But this is just an example. This can be applied actually for some other problems. Here we get a log n approximation for this problem. Of course, much worse than this 1.39. But there are the next problem that we talk about, group Steiner tree. Actually, the approach using this Bartal is the best that we can get it essentially. But there are several other problems that this is the best that we can get it is through this approach. Good. Let's continue this. So you are given this graph, as I mentioned. You can always consider this graph because if you want to connect this guy, you can just do pre-process. Any edge which is useless, that if there is not there, the distances will not go up. So you can always consider some kind of pre-processing that any edge that if you can delete it and the distances between any 2 vertices don't go up, just delete them. To consider this graph. Now, from this Elkin others that we discuss, or I will say actually no, with the Abraham, Bartal, and Newman, so ABN, we can get say polynomial number of trees. I think they may have more than n log n, but anyhow, say that we have polynomial, say n or order n, a number of trees, say T1, T2 to Tk, and as I mentioned, k is poly n. For Bartal is n log n, but here I think it is might be a bit more than that. Good. So we have these trees. Now in each of these trees, and these are spanning trees. So how can we solve the problem? So we will consider this first one, the second one, the third one. And see, this is the T1, T2 to Tk. So for each of these problems, these are these Steiner points that we have it, S1, S2, S3, and S4. And these are the spanning subtrees. So these vertices appear somewhere. And it is a tree. Okay, so how can we solve the problem? The problem becomes trivial, the Steiner points, because any points, essentially any edge, which is useless in this tree, it means that it will, if we delete it, still these guys are connected. Of course, this is a spanning tree, so we know that all of them are connected, all these Steiner. Now, you just consider each of them. If there is one vertex, one edge that you can delete and still all these guys are connected, just delete it. So you will find a solution for this one, for this one, for this one, and then you just take the best of these trees, the best solutions, and that you will output it. And of course, it is a solution because it's a spanning tree. If it was FRT, you need to be a bit careful because it's not necessarily a solution, but we will talk about it. But for now, you will just find this trees, T1, T2, Tn. The Steiner tree problem on each of them would be trivial problem. You just find it, and then you will output the best solution. And you want to say that this is the log n approximation of the original. And actually, we have implemented that. Some of this, actually, we have implemented this type of algorithm at Google, and it was working very well. So in practice, it would be not log n. In the worst case, it's log n, but can be much better than good. Now, what do we want to show? That we want to say that if we consider the solution, then say, I mean, one of these guys is minimum. So say this is the guy that is the minimum, this is the solution, and the cost of that is C. We want to show that C is less than this parameter. And say this is just alpha. As I mentioned, we are considering alpha to be log n for now, or O tilde log n. So we want to say that it is alpha times opt of the original best Steiner tree in the graph. Okay, so that's an algorithm, very simple algorithm. That's typically the thing. So we are just getting essentially the problem. We are assuming this is a tree. We solve the problem on trees, and then we are done. Okay. Great. So the main equation, this is a very important equation because these problems, and again, this is the way that I'm presenting for a Steiner tree, but exactly the same thing works for all connectivity problems when we probabilistic embedding into trees. And not only that, but also for the cut problems that I will talk next. But before going through that, I wanted to, mention this one such that we go through once and see what is the way that we can do it. So how can we argue? Let opt-G be the solution and its cost in graph G. As I mentioned, whenever we talk about opt means two things: the solution itself and the cost of the solution. So this is opt-G. This is the opt-G for the problem that we are considering. In this case, is a Steiner tree on the graph. Again, you want to connect a set of Steiner points in a graph with the minimum total cost. Now, consider each edge of the optimum. So this opt-G, a set of, this is, of course, the solution should be a tree. Otherwise, you can delete a set of wedges. Generally, in the connectivity problem, you can assume that the solution is a tree, because otherwise you can just delete the edges and you get not worse solutions. This is the problem. You consider an edge E. You need to massage this opt and somehow connect it with the optimum solutions on each of these trees. This edge E may not exist in one of these trees, or maybe in some of these trees. So from opt-G, we want to find a solution. So, and these are the trees that we have. This is the T1, T2, say TK. So consider an edge in the opt. The issue is that in this tree, say this is the thing. This is between two vertices U and V. This, so we want to find a solution in T1. How can we find a solution? This edge UV may not exist in this tree T1. That's the thing that we try to smear this edge essentially into the path in this tree. So how can we do that? So consider this edge. I will say, okay, U is here, V is here. Maybe they don't have any edge here, but there is a path between them. I will buy all these paths. And again, buy means essentially selecting those edges. So that's UV. Then there is another guy, maybe this is from V to V prime here. Maybe V to W. Then this case, I will say, okay, this is W is here as well. I will buy also this path. And again, some edges we may buy twice. We don't care. So for each edge in the optimum, I will buy the corresponding path in this tree. And of course, this is the tree T1. We can do it for all these trees. What do we have? As a result, we know that after we are doing all of them, we obtain a solution on each of these trees. The tree T1, tree T2, to tree T3. Because all connectivity has been done. And of course, we have used maybe one edge more than once. You can just delete the copies, of course. But say even we keep those edges, see what will happen. So from each of these guys, I will get opt-I. Opt-I is the mapping of opt, in some sense, mapping of opt into tree TI. So in TI, we have the opt-I. So also in each of these, so we have TI, opt-I, and we have CI. CI is the optimum on this tree T. So CI, I will say opt in. So so we have from opt, we have a mapping on TI, which is opt-I. But at the same time, we have also CI. What is CI? CI is the optimum on this particular tree. The way that actually, the way that we solved the Steiner tree on each of them, and we just removed unnecessary edges. From that, we can get the C. And what is CI? And what is C? C was the essentially mean of CI. So as I mentioned, a Steiner tree actually on each of these problems, on each of these three can be solved trivially, and we can get the optimum solution. That would be CI, and we take the minimum of them as a solution. So C is equal to mean of CI. So we have opt-I and we have CI on each TI. Now let's write the equations. What do we want to see? As I mentioned, this is alpha. Whatever alpha is, like essentially O tilde log n. So we want to say that C is at most alpha times opt of G. So the solution that we found and we report, we want to say it is comparable with. This is essentially the whole equations. So this is again alpha. So we know that alpha times opt of G is greater than or equal to this. I equal to 1 to K Pi times opt of Ti. Why do we have this? Note that each edge of opt here, for each edge of, essentially for each edge of opt here, we know that like if we consider this edge, the distance is exactly the set of edges that we bought it here. For each edge here, if you consider the distances over all of them, and then times the probability, that would be less than alpha times that original distance. So we just sum it up over all edges of the optimum, the paths that we are buying in each of these trees. And that would be the distance on that tree. And if we multiply by the probability, that is at most alpha times opt of G. This is by definition of the probabilistic trees by definition of embedding into probabilistic trees. So this one is just by summing over all edges. And then you will consider the opt-I. For opt-I, we didn't do any optimization. We just consider some of these distances. Now, what do we have after that? So this is the PI. Now, we know that opt-I is just one solution. It is a solution here. And of course, it should be greater than or equal to the optimum solution. Optimum solution in this case would be CI. Again, for this problem, for example, for Steiner tree, this is a very simple problem that we just do it trivially, the solutions. But some other like group Steiner tree actually is non-trivial, even on trees. But when we solve on the tree, we know that opt-I is greater than CI. Because that is a solution, this is the optimum solution. as we have mentioned here. Now, we know that the C was the mean of Ci's because we took the minimum of them. So instead of all these Ci's, I can just put C. And then C is a constant that comes out of this equation, and it would be just the sum of the PI's. And we know that it's a probability distribution over trees, so sum of the PI's would be equal to 1. So that would be equal to C. So we have obtained that alpha times opt of G is greater than or equal to C. It means that C is at most alpha times opt of G. This is things that we are using for all sorts of problems, not only for cut problems, but for the connectivity problem. Everything comes out of these equations, set of equations. I don't repeat it essentially, but that's the whole idea that we are doing that. Now, what about if we want to use FRT instead of C? So if we want to, instead of this essentially Abraham, this probabilistic into a spanning trees. So in the FRT, the issue is that this solution C that we have, again, we are saying both the cost and the solution C. This C these edges that exist in C, so you obtain some solution. But the issue that is tree that you have, that does not exist in the graph. So how can you translate these things essentially to the original graph? That would be easy. So again, we are doing the same thing that we had done for opt. We said, okay, this is a tree. This is my solution essentially. So I have connected these guys essentially UV. Just instead of this UV, this is a tree. Just by the corresponding path in the graph, or the shortest path actually. What will happen? We have this expansiveness property. So we mentioned that if these are spanning trees, expansiveness comes for trivially because, of course, I mean, if you consider a spanning tree of a graph, that any shortest path between any path or the length of the path on this tree would be greater or equal to the original distance. But even if these are not subtrees, because we have expansiveness, we know that between U and V, the distance in this tree is greater than or equal to the original distance in the graph, that by expansiveness. So instead of UV, yes, it may not exist this edge there, but just by the shortest path there. The solution can only go down. And of course, you will even delete some of these. Some edges may repeat and you can delete them. But because of expansiveness, so when you obtain the solution, then the solution can only go down. So you get so you may get another solution C prime in the original graph if C is in this probabilistic embedding trees like FRT, but we know that C prime is also less than or equal to C. So still we get a solution which is. So this problem, I mean, this is the approach that you are using it essentially for almost all problems that you can solve them on the trees. For example, if you consider instead of a Steiner tree problem, if you consider a Steiner forest problem, in which we don't want to, I mean, so in the Steiner tree, we had set of Steiner points that we want to connect them to each other. In the Steiner forest, we want to actually, we have S1, T1, S2, T2, SK, TK. And I want to just connect S1 to T1, S2 to TK, and to T2 and SK to TK. Hello. So I don't necessarily want to connect T1 to S2. This problem called Steiner forest, you don't want to connect everything together, but you want to have the pairs, essentially, the multi-commodity version. For this problem, I mean, the best thing actually is a two approximation. And it is a very big open problem whether you can improve these two. But again, using this approach, you can get a simple Laguerre approximation because exactly the same thing. What do you do again? You will consider this one. You consider each of these trees. In each of these trees, you just connect these guys because again, you can delete those edges which are not useful, and then you get a solution exactly the same equation that I have mentioned. You can write it, and then you can get Laguerre. So sometimes this problem called generalized Steiner tree. Originally, I think by Gomez and Williamson, it is called generalized Steiner tree, but it is nowadays it's called Steiner forest. Good. Good. So as I mentioned here, for Steiner tree, there is the best algorithm is 1.38. For Steiner forest is 2 minus 1 over n, but using this, you can get log n approximation. What about the directed graph? If you can define the same problem for directed graph. So it is called directed Steiner tree. What is a directed Steiner tree? You are given a graph which is a directed. And you want to find exactly, I mean, there's a root is given and you want to connect essentially this S1 to Sn to this root, or SK2. So this problem called the directed Steiner tree, because the graph is directed. Again, each edge is directed edge and has some cost that you need to pay. This problem is actually much harder. This is interesting. So for this problem, the best approximation is n to the epsilon. So for any epsilon, actually, you can get n to the epsilon. Big open problem. Can we get polylog for this? We don't know. But this Bartol thing does not work. Everything that we have mentioned is all this probabilistic embedding into trees are working only for undirected graph. So this is the, I mean, this is the way that I mentioned, two-word theory of everything, if you think about it. For undirected graph, we have a very good understanding nowadays. I mean, again, lots of work has happened this year, but we can consider this spanning trees and solve the problem and get it there. But for directed graph, essentially, none of this technique works and the problem becomes much harder. So it's a big open problem whether there is a polylog approximation for directed Steiner tree or not. Again, this problem, Steiner forest getting better than 2, or this one improving on these problems essentially for both of them. These are like you can get the best paper award in the top theory conference. What about a Steiner forest? For directed Steiner forest, again, this is a directed graph you want to connect from Si to Ti, S1 to T1, S2 to T2. This problem for this one, the hardness that we have is actually label cover hardness. We talk more about it if you go to my algorithmic lower bound course on my YouTube. Then we talk about it, and this is the label cover hard. So essentially, it means 2 to the log n to the 1 minus epsilon. If it was like it is, as I mentioned, it is omega of 2 to the log n to the 1 minus epsilon. So if you consider this one like 2 to the log n to the 1 minus epsilon would be n to the 1 minus epsilon, which is, of course, not correct. So this is not like that. But so essentially, this is, we know that, so it is the hardness. We cannot get this one. So the general conjecture is that you cannot get better, essentially, than some n to c for some constant c. So this is a bit weaker than this. So this is weaker than this, but the conjecture is that you cannot get better than n to the c for some constant c greater than 0. So you cannot get this n to the epsilon thing that we talked about it before. Again, these are all based on some complexity assumptions. So Steiner forest actually, the directed Steiner forest is a harder problem. That we know that. Directed Steiner tree, still we don't know this. Now, one problem in between is the group Steiner tree that we talk about it a few times before. Now I want to connect the dots for group Steiner tree. So again, what is the group Steiner tree? So in the group Steiner tree, you are given the sets S1, S2, S3 to SP of these vertices of the graph G. So you're essentially, each of them are the sets of the vertices. So all of them are subsets of P. The G of V at. The idea is that, and each edge again has some cost. You can even consider all the edges have cost one. These are some of the simple reduction. For example, you can say that, I mean, lots of problems, the edges have cost one. Yeah, as long as the edge weights are polynomial, you can assume this one. Or this kind of rooted versus unrooted. If the problem is unrooted, actually you can, always you can say that the rooted problem is like essentially a harder problem, because you can guess the roots, and then for each root you will solve the problem. These are simple things that you can think about. Now, here again, you can assume that the root is given to us or not, because you can always guess the root. Guess means trying all possibility and find it. So you want to find a tree that connects essentially one vertex. So like this is a terminal vertex, T1, T2, TP. You want to connect one vertex from each group. You can think about this S1, S2, SP. These are some of this backbone. They have some internal backbone that these guys are connected to each other. And we don't see it, but we know that they are connected. So here the idea is that I don't, as long as I can connect to one of these guys, then they are internally connected, everything will be connected. So this problem called group Steiner tree. So what is the best approximation that we have it for this problem? For group Steiner tree, on general graphs, the best thing that we have it is log n to the 3. How come? If you remember, I mentioned that. So again, first we can use Bartol or all of this FRT, etc. We can assume that we want to solve only the problem on trees, and then we will pay another log n factor more to get it. And if you have alpha approximation with the trees, the same alpha would be just multiplied in the final thing. So, and I don't repeat that one, exactly the same thing that we discussed before. Here, I just only need to solve the problem on trees, and I pay log n factor. But the problem on trees, if you remember, we already discussed that. This is the submodular tree coverage problem that we talked before. So we talk about submodular coverage for set cover, and then we mentioned there is a generalization of that. This is called submodular tree coverage. And for that problem, there is a log n to the 2 approximation. Submodular tree coverage actually is a tree problem. If you go back to the previous lectures, you can see that one. So for trees, there's a log n to the 2 approximation. Then to go to trees, you need to pay log n. So it would be log n to the 2 times log n would be log n to the 3. And that's the best thing for the group Steiner tree. Now, why group Steiner tree is especially interesting? Because this is a special case of directed Steiner tree. So how come? So consider this is the group Steiner tree. So this is the group that we have it. I want to create a directed instance. So this is the group. For example, these are the vertices. These are the vertices of the first group. Like this is A1, A2 to AH, and this is all of them. This is a group S1. So how do I do that? All edges of the graph that are here, I will put it by directed edges. So this is a typical thing, goes from undirected to directed. I will put both edges. If the edge here it had C, I will put the C here and C here. What about this? I will add some additional vertices. So this is the thing for this one. I will add another vertex S1, say, and I will put it just one way to this guys. And the cost of all these guys would be 0. So all edges in the graph are bidirected, but these edges are directed. Now you want to say this is a root and you want to connect everything to one vertex. Again, this root we can always guess because we can try all possibilities. So you now want to connect. So there is no, this is no group Steiner tree anymore. You only want to connect these additional vertices, S1, S2 to SK. You want that these guys are connected to the root. So we essentially remove the concept of group. And you know that S2, like S1 to connect, it needs to go through one of these guys and get connected. So it essentially satisfies this one. So group Steiner tree is a special case of directed Steiner tree for which we can get polylog approximation. So this was actually an open problem. Like, for example, for some graphs like for planar graphs, even directed planar graphs, that problem was quite open. But what about in these graphs? And there are some actually lower bound that was shown even for planar graphs in terms of integrality gap of the elements. And we have actually improved this group Steiner trees on planar graphs. And finally, it was a stock paper that we showed that for group Steiner tree on planar graphs, you can get actually p-tas, 1 plus epsilon approximation. So that's the ultimate result that you can get. However, for directed Steiner tree was open problem. That whether for directed Steiner tree on planar graphs, again, planar graphs are the graphs that there is no, all the edges can be drawn without intersecting each other on a plane. Can we get any result for planar directed Steiner tree, which is better than this n to the epsilon that exists for general graph? There's a paper actually in iCalc this year. I think it should have been actually a stock paper, but this was actually very nice and simple algorithm that is that you can get, I think, log n to the 2 or log n for directed Steiner tree on planar. So this was the open problem. They could actually solve it. However, the belief is that for planar directed Steiner tree, the problem should have a p-tas. That's the conjecture. But they could, but there was nothing known better than n to the epsilon, and they could actually show that it can get it log n to the, I think log n to the 2 or log n. So this was in this iCalc 2023. So for some special graphs, even the people don't know. But this group Steiner tree is like a very important problem because now it is somehow in between. Log n to the 3, can we improve it? This is a big open problem as well. We know that on trees is log n to the 2. And as I mentioned before, you know that on trees you cannot get log n to the 2 minus epsilon. This is not possible. Better than this for the on trees. However, actually, this was another, I think this was a Fox paper that we had this one, but they showed that actually you can get log n over log n. That is possible, log n to the 2 over log n. But not better than log n to the 2 minus epsilon for constant epsilon is not possible. On trees, group Steiner trees on trees. So group Steiner trees on trees. So that we can get it. But from general graphs, we don't know any direct way to show that it is log n to the 3. But like, we don't know whether log n to the 3 is the best things, or we can actually get it log n to the 2. I think the people, so it's essentially is that can we go around Barthol and do that or not? There are some problems for now, for those problems, we know that there is no way to go around Barthol. Barthol is the best that you can get. But there are some of them that maybe you can go around it. For example, for a Steiner tree, as I mentioned, we get log n through this approach, but you can directly actually get it just constant factor. So for some problem, this is the general idea. If you have some problem with this connectivity, you just use this machinery to get some things. And then the question that can you go beyond that? Sometimes you can, sometimes you cannot. So this is for group Steiner tree, as I mentioned, Steiner tree. A few other remarks I wanted to add. So Bartal, can we get probabilistic embedding into trees with distortion better than log n? It turns out there is no such, you cannot go better than log n. And the thing is come from this graph. This is a very famous graph. It is called diamond graph. This is a counterexample for lots of conjectures, actually. So consider this is like a fractal. So consider this square almost, or tilted square. All the things are one there. Then what do we do? I will just go there and then I will create this new graph, the same as before. Each edge I will put again a tilted graph. This is, as I mentioned, like fractals. I will put 1/2 here. I will do this one for all of these edges. And then I will repeat. So now instead of 1/2, I will put it to 1/4. I will delete the original vertices. So it is a fractal log n things that you will go there, log n depths you will go. Because to have it polynomial number of vertices, you can go log n depths essentially. Because each time the number of vertices essentially goes by constant factor. You go log n depths. This is the things that we call it, essentially this is the diamond graph. And this is, as I mentioned, counterexample for lots of problems, including Bartal. In this graph, there is no way that you can do it essentially probabilistic embedding into trees that the distortion is less than log n. And the proof, I mean, it's not that hard, but it's not trivial. I mean, you can search for it and then you will see. So this is the diamond graph, which is the important one. Again, this and what is the good thing about this diamond graph? This diamond graph, like if you want to draw it, like essentially in one, the level, I don't know, level 1 of these things would be something like this. So this is a very important thing, that this diamond graph is indeed a planar graph. And not only that, is a series parallel graph. So it has trivets too as well. So it's a very special graph, intersection of, it has good properties, and it is a counterexample for lots of problems. When you go depth log n, essentially. That's the thing that you should try always for some of the problem that you have. So that's about this one. Other things I wanted to add here. So far we have discussed about all of these problems for connectivity problems. What about for cut problems? So this was another interesting thing that, okay, so we get everything clean for connectivity. What about for cut problems? What is a cut problem? I mean, again, all of these problems that have a connectivity problem, you can consider the corresponding, all of this connectivity problem, you can consider the cut problem. For example, for the Steiner tree problem, it becomes the multi-way cut problem. What is the multi-way cut problem? So multi-way cut problem is that, so multi-way cut is that you are given again some of this S1, S2, 3, Sk. And you want to find a set of edges that if you delete these vertices, these guys, then all of these guys become disconnected. So minimum set of edges, the weight of those edges, you want to delete it from the graph such that all of them become disconnected. It's a problem called multi-way cut. There is a simple two approximation for that. Essentially, you just find the mean cut in the graph. So mean cut between, mean cut not necessarily, mean cut between two of these vertices, essentially. You cut it, and then you will repeat. And this gives a simple two approximation. Now, good. And I think we don't know whether we can get better than 2 for this or not in general. Again, for example, a Steiner tree, as I mentioned, in planar graph, a Steiner tree itself actually has a p-task. But as I mentioned, the group Steiner tree is a generalization of a Steiner tree because each of this group can have only one thing. That was somehow the current ultimate result that says that this problem also has a p-test on planar graphs. But directed one, which is a bit more general, we don't. Multi-way cut, this one also in planar graph, we showed that actually it has a p-test. But so this is the cut problem. So if you want to solve this problem, then the question is that what is the corresponding things here? Like we thought that, okay, you want to connect a set of vertices, consider a tree, and just solve the problem on trees. But what about cut problem? So how can we solve the problem for cut problems? The question is that the issue is that the tree, the same concept that, so what was the idea there is that for the connectivity problem, we just consider a spanning tree. And then we see that solving this spanning tree and the connectivity. But if you want to consider, of course, trees are still the easiest problem, easiest set of graphs that we can solve the problem. So we would like to actually solve the problem for trees on cut problems. However, if you have a general graph G, and you want to cut a set of vertices like this, then if I want to do this one, consider, so we can say this one, okay, find a tree in this graph. I say this is, I don't know, S1, S2, S3, and S4. This is S1, S2, 3, and this. So we say that find a tree and solve the problem on trees. But there's a problem because here, if I cut this edge of the tree, doesn't mean that I cut S1 and S2 in the graph G because they might have some other path. I just cut one path essentially. Even if it is a spanning tree of this thing, let alone if it is not a spanning. So the problem remains, essentially it was interesting that what can we do essentially for trees, for cut problems? Can we do anything for cut problems to solve them? Again, this kind of theory of everything. You want to solve the problem, solve it on trees. So there is nothing like other than trees that we can hope for. But trees does not work if we are doing this. However, there was this, I think the first one actually was by Rake. That was actually best paper award in Fox. That was a very nice result. And it was actually a stronger thing. So there are such of things that we will talk more about it, but I just want to say what is the tree that we can get it there essentially. So the catch is that if you have some edge here, so again, you can get this kind of things on the, so you can create consider some trees, indeed spanning trees. However, this is the main difference between the cut and connectivity problems. The issue is that, and it's come very naturally. So I want to make sure that when I cut this edge, say this is S1, this is say S5, for example. S1 and S5 are disconnected in the original graph as well. Otherwise, if I just put the edge of this, the weight of this edge, only the weight of this edge in the original graph, then I cut this one, I didn't cut those guys. So that's essentially the main thing, is that in the graph, what do we do? You can actually show that the weight, you can still create this one, and these are the spanning trees, but the only thing is that the weights are not just the weight of that edge. What is the weight? The weight would be the mean cut. So the weight of each edge would be the mean cut in the original graph between this part of the tree and the other part. So each edge in the tree, if you disconnect it, it has two connected components. See what is the mean cut between this connected component and this connected. This is the particular case of mean cut that you can solve it. What is the cut them? And that mean cut would be the weight of this guy. Then I can say that whenever I cut this edge, I will cut the corresponding cut in the original graph. This guy actually will be disconnected in the graph. That's essentially the state of the art. And interestingly, for the cut problem, as I mentioned, for connectivity problem, we cannot find one cut that can, like I cannot find one tree because the cycle CN I cannot do it with one tree. But for cut, we can actually have one tree only. Generally, cut problems are harder than connectivity problem. But in this case, interestingly, we don't have such a thing for connectivity things, but for cut, we can find even one cut, one tree, and put the edges like this. Here, the bounds would be a bit worse. We still have probabilistic into trees that gets log n, and that is somehow is a dual of Barthel. We will talk about it. But one tree, still you can get it. If the bounds is still a bit worse. Hopefully that bound also should be matched essentially log n, but we don't have that. This is again another very nice open problem. But then the rest essentially the same. So you can, this theory also can be applied for the cut problem. So this is somehow state of the art that now any cut problem you want to solve, again, you will consider the tree with these weights that exist, and then you will solve it on those trees, take the minimum solution. And you know that because of the definition of this phase, you can find a solution in the graph, and there is a log n approximation. Interestingly, this is for the bisection problem. This is the best solution that we can get it as well. There was a Fox paper, very complicated problem for the bisection. Essentially, the bisection is that you are given a sort of, you want to find a cut that almost cut the graph in half, like ceiling of n over 2 vertices in one side and floor of n over 2 vertices in the other side. How can we find it? The best algorithm actually using this. It was a very complicated algorithm before. Using this tree, actually, you can get log n approximation by some. Again, this connectivity cut problem, you can solve it by dynamic programming on trees. So that's currently essentially the state of the situation. Very nice. Again, this, if we can get one tree with the best bound would be the best, but we don't have it yet. So I will continue more. I will talk about now more proofs of this. The proof ideas are interesting. And as the cut problem actually also, it turns out to be dual of the connectivity problem. So we talk about all of this and the approaches. But here is somehow, if you want to solve your problem, take your favorite problem, bring your own problem, solve it essentially on the tree or the cut or connectivity, and you get log n approximation. Then the question is that, I mean, if you don't know, the people actually spend a lot of time to improve the algorithm to get the first algorithm. But if you know this theory, you just bring it, you get something. It is some good chance or high chance that maybe that's the best that you can do that. But then the question is that if it is not the best, can you get anything better? And that's the current state of the art, like makes it very clean for lots of network design problems. So lots of network design problems can be actually considered even like this kind of coverage problem that we talk about, set cover type of things, or this kind of cut or connectivity problem that we can solve them using this approach. There are still matching. For matching, there are some maybe ad hoc approaches, but this is such kind of general approach. And of course, now improving over this bound would be very nice. Good. So I think we will continue next time with more problems and the FRT and the proof of that. But I just want to give you some ideas about the whole things.